Way back during the summer of 1977, inside a dimly lit pub tucked away on the quiet edges of Geneva, a young physicist by the name of John Ellis happened to lose a game of darts. His challenger across the board was a visiting student known as Melissa Franklin, and the stakes of their little wager were delightfully simple. If Ellis suffered defeat, he was required to work a specific word into his next serious academic publication, and that word was penguin. True to his word, when he found himself crafting a dense, highly technical paper detailing the intricate decay pathways of quarks, one of the foremost theoretical minds at CERN sketched out a visual representation of subatomic particles morphing into one another, stared closely at the peculiar geometry of the lines, and deliberately named the shape after a flightless aquatic bird. It was meant as nothing more than an inside joke, a light-hearted nod honored by a scientist gifted with a genuine sense of humor. And surely not a soul in that tavern could have foreseen that half a century down the line, the most profound and unsettling number in all of modern physics would trace the silhouette of a penguin. Today, situated deep beneath the rolling borderland shared by France and Switzerland, lies the largest and most complex scientific instrument ever engineered by humanity. Encased in a massive underground ring of superconducting magnets measuring 27 kilometers in circumference, dual beams of protons race in opposite directions, completing 11,245 laps every single second while hurtling through space at 99.99999% of the speed of light. To keep these beams on track, the steering magnets are chilled down to 1.9 degrees above absolute zero, rendering the interior of the Large Hadron Collider significantly colder than the empty expanses of intergalactic space. When these opposing streams of matter cross paths, protons smash into one another hundreds of millions of times with every passing second, briefly recreating the furnace-like conditions that characterize the universe less than a billionth of a second after the dawn of the Big Bang. This colossal machine was brought into existence through the collaborative efforts of more than 10,000 dedicated individuals hailing from over 100 countries, all united by a singular ambition: to break physics. They built it to slam matter together with such cataclysmic violence that something entirely unprecedented might rattle loose, something that defies the predictions of existing mathematical frameworks. And to comprehend why anyone would invest decades of their life and billions of dollars in an effort to shatter the laws of physics, one must first appreciate the staggering elegance of what they are attempting to crack. This intellectual monument is known as the Standard Model, and it stands quietly as perhaps the single greatest achievement of human reasoning. It accounts for every fundamental particle ever discovered, alongside 3 of the 4 fundamental forces governing nature, fitting neatly onto a single page of text while retaining a level of precision that routinely stretches human intuition to its absolute limits. When theoretical physicists utilize the Standard Model to calculate the subtle magnetic behavior of an electron, and subsequently test that prediction in a laboratory setting, the theoretical calculation and the empirical measurement match up to an astonishing margin of roughly 1 part in a trillion. To put that into perspective, it is equivalent to predicting the exact distance separating New York City from Los Angeles and getting the calculation right down to the width of a single microscopic bacterium. No other intellectual framework in the history of science has ever undergone such rigorous testing across so many varied scenarios for such an extended duration, and no theory has ever won its battles so relentlessly. For 50 years, every particle accelerator, every delicate detector, and every meticulous measurement has returned the exact same verdict, confirming that the Standard Model is correct once again. To conventional physics, that sort of unbroken streak sounds like the ultimate triumph, but over time it has morphed into a slow-moving nightmare, because the Standard Model fundamentally cannot represent the entirety of reality. For all its breathtaking accuracy, it remains glaringly incomplete. It possesses absolutely nothing to say about gravity, offers no explanation for dark matter, the invisible substance whose gravitational grip shapes the architecture of every galaxy in the cosmos, and stays entirely silent on dark energy, the mysterious force accelerating the expansion of the universe. It fails to account for why neutrinos possess mass, and most hauntingly, it cannot answer the most fundamental question of existence: why there is something rather than nothing at all. At the moment of the Big Bang, matter and antimatter ought to have been forged in precisely identical proportions, leading to total annihilation that would have left behind a universe composed entirely of pure light and absolute emptiness, which is precisely what the Standard Model dictates should have happened. Instead, for every billion particles of antimatter produced in that primordial flash, the universe managed to spit out 1,000,000,001 particles of matter, and that single leftover particle in every billion is everything we know. Every star blazing in the night sky, every swirling galaxy, every rocky planet, and every single atom making up the reader's body is forged entirely from that minuscule surplus that theoretically should never have survived. The Standard Model is a flawless description of a universe that should be completely empty, which proves beyond a shadow of a doubt that it is fundamentally broken, or at least profoundly unfinished, harboring missing particles, hidden forces, and undiscovered laws waiting just beyond the horizon of its equations. The frustrating reality is that for half a century, the theory has stubbornly refused to offer any clues about where researchers ought to look next, leaving every door pushed by physicists to reveal nothing more than solid stone. An entire generation of researchers has spent their entire professional lives pressing their palms against those cold barriers, desperately searching for the slightest hint of a draft. And over the past 3 years, in one specific corner of experimental particle physics, within a specialized process tracing back to a Geneva dart game in 1977, they have finally started to feel a breeze. Stationed at a specific point along the colossal ring near the French village of Ferney-Voltaire sits a specialized detector known as LHCb, spanning 21 meters of high-precision silicon, tungsten, and steel. Unlike its more famous siblings Atlas and CMS, which hunt for new physics through sheer brute force collisions, LHCb was engineered for subtler investigations, functioning as a delicate precision instrument devoted entirely to a single letter of the alphabet, the letter B. It continuously monitors the fleeting births and catastrophic deaths of particles known as B mesons, fragile entities containing a beauty quark that manage to exist for roughly 1.5 trillionths of a second before disintegrating into other forms. During that unimaginably brief existence, a B meson performs intricate quantum experiments entirely on its own, a process that represents the single most vital concept in this entire narrative. When a B meson decays, the transformation occurs via a quantum loop, a transient bridge where particles that do not officially exist in the macroscopic world flicker in and out of reality, recognized in physics as virtual particles. For an instant too brief for conventional instruments to measure, the decaying particle borrows matter from the vacuum, any particles whatsoever, including exotic varieties that human science has never formally discovered, uses them to execute the transformation, and returns them to the vacuum before the universe ever notices. The Feynman diagram mapping this bizarre loop is none other than the penguin John Ellis sketched out decades ago, turning these specific decays into something akin to magic, a specialized microscope aimed directly at the unknown. If an undiscovered particle exists in nature, even one far too massive for the Large Hadron Collider to manufacture outright, it can still manifest momentarily inside that quantum loop as a ghostly presence, leaving behind a subtle fingerprint in the form of tiny shifts in angular distributions and minute changes in energy states. The decay itself transforms into a measuring apparatus sensitive to physics operating at energy scales that no machine built by human hands could ever directly reach, allowing researchers to spot the shadow of a monster passing across the surface of deep water, even if the creature itself remains unseen. This is what LHCb watches for, focusing intently on a vanishingly rare decay pathway where a B meson transforms into a kaon, a pion, and 2 muons, a sequence that occurs roughly once out of every million B meson deaths. To investigate this extreme rarity, analysts sifted through 650 billion recorded decay events gathered between 2011 and 2018, hunting for a handful of needles scattered across a mountainous hayfield. Before diving into the data, The collaboration executed a procedure that outsiders rarely hear about, a testament to how deeply particle physicists fear fooling themselves. They blinded the analysis. For years, the team examining this specific decay was strictly forbidden by their own procedural rules from looking at the actual final answer, calibrating their instruments, modeling potential backgrounds, and rehearsing every step of the measurement, while the definitive result remained locked away in encrypted software files. This practice of blinding is how modern science protects itself from human hope, ensuring researchers do not unconsciously steer their methods toward a desired outcome. When the software box was finally unlocked in an ordinary conference room surrounded by laptops and coffee cups, years of meticulous labor compressed into a single keystroke, revealing a plot on a projector screen that exposed what the universe had been hiding. The measured angles were wrong, displaying a precise, persistent deviation that leaned stubbornly away from the standard model predictions, without fading as the dataset expanded. When the collaboration published their full analysis in physical review letters, the statistical discrepancy stood at 4 standard deviations, meaning that if the standard model is entirely correct and the anomaly is nothing more than random statistical noise, the odds of encountering a fluctuation this extreme by pure chance are roughly 1 in 16,000. In the realm of particle physics, 4 sigma does not quite cross the rigorous threshold required to claim an official discovery, which demands 5 sigma odds of about 1 in 1.7 million. Instead, 4 sigma operates like a heavy hand pressing against your shoulder in a dark room, demanding an explanation while refusing to reveal whose hand is resting there. What elevates this particular 4 sigma signal above the hundreds of forgotten anomalies of the past is that it does not stand alone. In the previous year, the CMS experiment, a completely separate detector situated on the opposite side of the 27-kilometer ring, operated by an entirely independent team utilizing distinct hardware, distinct software, and separate blind spots, published its own independent measurement of the identical decay channel, revealing the exact same lean toward the unknown. 2 distinct machines, run by rival teams striving to prove each other wrong, observed the exact same subtle tilt in the exact same physical process. Furthermore, this specific decay channel has been whispering hints for well over a decade, with the earliest anomalies surfacing in 2013 within an obscure observable designated as P5 prime. That structural anomaly was present in the initial dataset, persisted when the volume of data doubled, remained visible through subsequent upgrades, and has now been sharpened and refined through years of continuous collider operations, never once vanishing into nothingness and never quite growing into an undeniable discovery. It sits in the data like an unyielding splinter at the very edge of what the standard model is mathematically capable of absorbing. This leaves science staring down a sharp dilemma, mirroring the finest mysteries in academic history. Either the most successful theoretical framework ever devised is quietly failing in one very specific process, offering our first direct glimpse of a reality stretching beyond our current comprehension, or something mundane is managing to fool 2 massive experiments, thousands of trained scientists, and 12 consecutive years of accumulated data simultaneously. There exists one additional possibility that frequently robs theoretical physicists of their sleep, revolving around the reality that the penguin loop is not entirely empty even within the standard framework, as it can be populated by ordinary charm quarks whose intricate behaviors are notoriously difficult to compute, earning them the whimsical designation of charming penguins among researchers. Should these charming contributions prove significantly stronger than current computational methods can accurately predict, they might successfully mimic the exact signature of new physics, rendering the perceived crack in the wall nothing more than an optical illusion cast by our own theoretical reflections. To determine whether this persistent signal represents a brand new law of nature or merely a bird-shaped illusion woven by behaving quarks, one must first confront something considerably darker by exploring the graveyard of physics, examining how many times researchers have stood in this exact position before, certain they were gazing into the future, only for the anomaly to wither away. Physics maintains a quiet graveyard that never appears in glossy textbooks or commemorative plaques at CERN, serving as the final resting place for once celebrated anomalies that promise to revolutionize science before dissolving into loose cables, statistical coincidences, and overlooked calibration corrections. Anyone examining a potential crack must first walk through this graveyard because the scientists finding these signals have walked its paths repeatedly, which explains why their hands remain steady and why their cautious warnings carry such profound weight. Consider the loudest ghost of modern scientific history. In September of 2011, an experiment known as Opera, buried deep beneath the Gran Sasso Massif in Italy, announced a result that should have been physically impossible, claiming that neutrinos fired through the Earth from a CERN facility 730 kilometers away were arriving 60 billionths of a second too early, effectively traveling faster than the speed of light. That measurement stood proudly at 6 standard deviations, representing a level of statistical confidence far surpassing conventional discovery thresholds, threatening to upend Einstein's relativity and throw causality into chaos. Global headlines erupted, and the research team invited the scientific community to prove them wrong, only for technicians to discover 5 months later that a single fiber or optic connector linked to a GPS timing receiver had worked itself loose, introducing a tiny delay that manufactured the illusion of faster-than-light particles. The spokesperson resigned, the correction was formally published, and the physics community relearned its oldest cautionary tale. 6 sigma of statistical confidence means absolutely nothing if the fundamental error resides not in your math, but in your underlying hardware assumptions. A stranger ghost emerged in December of 2015 when the 2 giant detectors at the Large Hadron Collider independently reported an unexpected excess of photon pairs, revealing a sharp bump in collision data at an energy level of 750 gigaelectron volts that looked precisely like the signature of a brand new particle. Theoretical physicists instantly lost their collective composure, churning out over 500 academic papers in the span of several months, attempting to decode the properties of a hypothetical object that nobody had actually confirmed. By August of the following year, once additional collision data had been processed, both detectors revisited the measurement and discovered that the bump had completely vanished, leaving behind no profound explanation or reinterpretation, but simply fading away as if it had never existed. It was nothing more than the universe rolling dice and 2 independent teams accidentally watching the same random combination land simultaneously, delivering a harsh reminder that even 2 separate experiments agreeing with one another does not constitute absolute proof when statistics conspire. The third ghost did not perish due to hardware failure or a roll of cosmic dice, but fell victim to something far more subtle and unsettling, haunting the present discussion more directly than any other. For 2 decades, the most famous anomaly in particle physics centered upon the magnetic wobble of the muon, the heavier sibling of the electron whose magnetic behavior is predicted by the Standard Model with extreme precision. Back in 2001, an experiment conducted at Brookhaven National Laboratory measured that wobble and found it slightly stronger than anticipated, hovering around 3 sigma for 20 years. Fermilab eventually rebuilt the experiment around a massive 15-meter magnet ring transported across America, and by 2021 delivered a headline-grabbing verdict placing the anomaly at 4.2 sigma, eventually crossing the 5 sigma threshold by 2023, with a precision measurement confirmed in 2025. Yet that anomaly effectively dissolved anyway because while experimentalists were perfecting their instruments, theorists were discovering that the theoretical prediction itself was fundamentally flawed. The immensely difficult task of computing the muon's wobble involves calculating the murky quantum froth of quarks and gluons, which for decades had been approximated using indirect data, until advanced supercomputers running lattice QCD became powerful enough to calculate the values from first principles, shifting the theoretical prediction directly toward the experimental measurement and collapsing the discrepancy into insignificance. 20 years of hope were erased not by a superior experiment, but by a better calculation, proving that the goalposts had been standing in the wrong place all along. Then there is the fourth ghost, buried closest to home, because the very family of B meson decays under scrutiny had already produced a legendary irregularity known as the RK anomaly. The standard model relies upon a structural pillar called lepton universality, asserting that electrons and muons, which share identical properties apart from their mass, must be produced at precisely equal rates in rare decays. For nearly a decade, B meson data suggested this rule was being broken, indicating that these particles were generating fewer muons than electrons, reaching a statistical significance of 3.1 sigma in 2021. Theorists rushed to assemble global models where a single new force explained everything at once, only for LHCb to announce in late 2022 that the measurement was fundamentally contaminated by background particles masquerading as electrons due to imperfect algorithmic identification. Once that contamination was cleaned up, the electron-muon asymmetry evaporated, snapping the ratio back to standard predictions and erasing 8 years of intensive research programs in a single seminar. This accumulated graveyard of a loose cable, a statistical fluke, a miscalculated prediction, and a contaminated background represents the gauntlet that any claim of a new physics crack must survive, making the current situation genuinely bizarre. The angular anomaly has been dragged through every single one of those historical exits and has successfully refused them all. Could it be an instrumental artifact or systematic hardware flaw unique to one machine? That explanation lost its footing when CMS independently verified the same lean using completely distinct hardware and calibration methods. Could it be a statistical ghost like the short-lived diphoton bump? That bump disintegrated under fresh data, whereas the angular anomaly has survived 4 separate expansions of data across 12 years without fading. Could it be background contamination like the RK saga? The collaboration applied their harshest analytical knives to the muon decay channels, utilizing cleaner backgrounds and rigorous modeling that failed to unearth any mundane contamination. This leaves the lingering possibility of the charming penguins, the theoretical map of the wall being miscalculated due to the complex behaviors of charm quarks circulating within the quantum loop. While theorists continue pushing their computations to the limit, current calculations indicate that charm contributions alone fall short of bending the angles as drastically as detectors observe, though the uncertainty has not yet been entirely strangled. Furthermore, an entirely separate family of B meson measurements involving the tau lepton, the heavy sibling of the electron, has likewise been drifting from standard predictions at roughly 3 sigma, rhyming with the angular anomaly by pointing directly at the same structural promise of lepton universality. When 2 distinct anomalies lean against the same hidden architectural beam from opposing corners, they begin to resemble a genuine structure rather than an isolated splinter. If these anomalies continue holding their ground while theoretical calculations close in, what kind of entity might be lurking inside that quantum loop? The leading suspects carry profound implications for our understanding of reality. The first candidate is a leptoquark, a hypothetical particle that bridges the rigid barrier separating quarks, the building blocks of protons and neutrons, from leptons like electrons and muons, which function as separate kingdoms within the standard model. Discovering a leptoquark would imply that these 2 distinct families of matter are actually branches descending from a single deeper structure, offering the first tangible evidence for grand unification. The second candidate is a Z-prime boson, representing a brand new fundamental force of nature that selectively interacts with matter by distinguishing between an electron and a muon in ways no known force unforced does, serving as our first contact with an invisible interaction operating beyond the energy reach of any human machine. History teaches us to pay close attention to small, stubborn numbers that refuse to die, mirroring the 19th century mystery of Mercury's orbital precession, where a tiny discrepancy in the planet's closest approach to the sun baffled astronomers who spent decades fruitlessly searching for a hypothetical planet named Vulcan inside its orbit. Those mundane explanations ultimately failed, and the anomaly was revealed not as a missing planet, but as the first crack in Newtonian physics, welcoming the dawn of general relativity. Small, stubborn numbers that survive every attempt to dismantle them are simply how reality communicates that it extends far beyond the boundaries of the intellectual rooms we construct. And if the persistent leaning angles observed in the decay of B mesons ultimately survive the final trials of theoretical computation, they may well represent the vital crack through which the next great era of human understanding finally steps into the light. To fully appreciate the magnitude of what these anomalies imply, one must look beyond the immediate boundaries of particle collisions and consider the deep structural silence of the theoretical framework that has governed modern science for half a century. The Standard Model is a monument to human ingenuity, yet it resembles an exquisite map of a coastline that completely omits the vast, uncharted ocean lying just beyond the surf. It maps the known particles with breathtaking precision, cataloging every quark, lepton, and gauge boson with names like up, down, charm, strange, top, bottom, electron, muon, tau, photon, gluon, and the Higgs boson, assigning each a precise mass, charge, and spin. Yet, when we ask why these specific particles exist in these exact masses and quantities, the theory offers a profound, deafening silence. It treats these fundamental parameters not as values to be derived from deeper principles, but as arbitrary numbers that must be plugged in by hand from experimental measurements, akin to building a magnificent clockwork mechanism while leaving the key structural gears entirely unexplained. Consider the sheer mystery of the three generations of matter, a bizarre architectural choice embedded in the very foundation of subatomic physics. Every stable atom in the universe, every carbon atom in our DNA, every oxygen atom we breathe, and every iron atom in our blood is constructed entirely from particles belonging to the first generation, up quarks, down quarks, and electrons. The second and third generations, consisting of heavier siblings like strange and charm quarks, muons, taus, and beauty quarks, are utterly unnecessary for the construction of ordinary chemistry or everyday life. They are unstable, fleeting entities that decay rapidly into lighter forms, yet nature has replicated the exact same quantum blueprint 3 distinct times, scaling up the mass with each iteration, while keeping every other fundamental property identical. The Standard Model possesses no theoretical mechanism to explain why there are 3 generations rather than 1, 4, or an infinite number, leaving this profound repetition of matter as an open wound at the center of modern particle physics. This exact structural mystery is known as the flavor puzzle, and it is precisely where the penguin diagrams and B meson decays strike their blow. The word flavor in physics refers to the distinct types of quarks and leptons, and flavor physics is the study of how these different types transform into one another through the weak nuclear force. In the Standard Model, these flavor transformations are governed by a complex mathematical matrix known as the Kabibo-Kobayashi-Maskawa matrix, which dictates the probability that a quark of one flavor will spontaneously morph into a quark of another flavor. This matrix contains built-in parameters that account for the subtle asymmetries between matter and antimatter, known as CP violation. Yet when physicists tally up the amount of CP violation generated by these known pathways, it falls short by many orders of magnitude. The amount of asymmetry written into the equations of the Standard Model is completely inadequate to explain why a universe born in total symmetry ended up leaving behind a surplus of matter capable of forming stars, galaxies, and living beings. This brings us back to the core of why the anomalies observed at the Large Hadron Collider carry such existential weight for contemporary researchers. The deviations appearing in the rare decays of B mesons do not occur in random background processes. They happen precisely within the flavor sector, right at the delicate machinery where one generation of matter transforms into another, and where the strict rules governing lepton universality are supposed to be enforced without exception. When an experiment like LHCb observes beauty quarks decaying through a quantum loop, they are peering directly into the engine room of flavor physics. If an undiscovered heavy particle or a hidden fifth force is modifying these pathways, it acts as a selective filter that alters the behavior of muons while leaving electrons untouched, or shifts the angular distributions of decay products away from theoretical predictions. It targets the very structural seams where the standard model is most vulnerable, exploiting the exact mathematical tensions that theorists have wrestled with for decades. To understand how physicists hope to resolve this tension, one must examine the painstaking interplay between experimental detectors and theoretical calculations. On the experimental side, the international collaborations operating detectors like LHCb and CMS are locked in a relentless pursuit of statistical certainty, upgrading their electronics, refining their particle identification algorithms, and gathering massive new datasets during successive runs of the Large Hadron Collider. Every recorded collision is subjected to rigorous, multi-layered scrutiny designed to eliminate every conceivable source of human bias, instrumental drift, and background contamination. When a collaboration publishes a measurement carrying a 4 sigma deviation, they do so only after exhausting every internal mechanism to make the signal disappear. They want the anomaly to be false because false anomalies lead to wasted years and broken careers, which is precisely why survival against this level of institutional skepticism gives the remaining signals their undeniable gravity. On the theoretical side, the burden of proof is equally crushing, driven by the race to tame the charming penguins and other complex quantum phenomena that threaten to mimic new physics through sheer computational opacity. The mathematics of quantum chromodynamics, the theory describing the strong nuclear force that binds quarks together, is notoriously difficult to solve analytically because the force carriers, gluons, interact with one another in fiercely nonlinear ways. For generations, calculating the behavior of virtual charm quarks circulating inside a penguin loop required heavy reliance on approximations, models, and indirect inferences drawn from complementary measurements. Today, theoretical physicists are deploying massive supercomputer clusters running lattice QCD simulations, discretizing spacetime into a 4-dimensional grid of points and computing the interactions of quarks and gluons from first principles. As these lattice calculations grow more refined and powerful, they tighten the noose around theoretical uncertainty, steadily clarifying whether the charm quark contributions are truly powerful enough to bend the decay angles on their own, or whether they fall short, leaving the door wide open for undiscovered particles. Should the theoretical calculations ultimately confirm that the charming penguins cannot account for the observed deviation, and should the experimental significance cross the sacred 5 sigma threshold required for a formal discovery, the philosophical and scientific landscape of physics will undergo a seismic shift. The confirmation of a leptoquark, for instance, would do far more than simply add a new entry to the particle data group tables. It would validate decades of theoretical speculation regarding grand unified theories. For half a century, physicists have dreamed of merging 3 of the fundamental forces of nature, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single, elegant mathematical framework operating at unimaginably high energy scales, an era known as the Grand Unification Epoch that existed during the earliest fractions of a second after the Big Bang. At those extreme temperatures, the 3 forces are predicted to fuse into a unified force, and the distinction between quarks and leptons dissolves entirely, allowing them to transform into one another freely. Discovering a low-mass leptoquark, operating as a virtual ghost in a penguin loop, would serve as tangible, low-energy shrapnel from that high-energy unification, providing the first experimental anchor for theories that have spent decades adrift in pure mathematics. Alternatively, the identification of a Z-prime boson would signal the arrival of an entirely new fundamental force of nature, expanding our understanding of the cosmos beyond the familiar quartet of gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Unlike gravity, which pulls on all mass universally, or electromagnetism, which acts on all electrical charge, a Z-prime force could possess selective couplings, interacting exclusively with specific generations of matter, or ignoring certain particles entirely while exerting a powerful influence on others. Unveiling a hidden fifth force would completely rewrite our view of the subatomic landscape, suggesting that the universe we observe is merely the local manifestation of a much richer, more intricate tapestry of interactions operating just out of reach of our conventional instruments. It would transform our understanding of dark sectors, potentially offering a portal through which normal matter can communicate with the elusive dark matter that constitutes the vast majority of the universe's mass. Yet, even as these grand possibilities hang in the balance, the seasoned veterans of particle physics remain acutely aware of the historical ghosts that litter the discipline's past. The graveyard of anomalies is a constant reminder that nature possesses an infinite capacity to surprise us with mundane deceptions, whether through a loose fiber optic cable mimicking faster than light neutrinos, a statistical fluctuation creating the fleeting illusion of a diphoton resonance, an incomplete theoretical prediction masking the true behavior of quantum froth, or an overlooked background contamination masquerading as lepton universality violation. Every single one of these historical phantoms looked terrifyingly real to the researchers who first encountered them, generating intense excitement, countless academic papers, and sweeping headlines across global media outlets before ultimately dissolving into ordinary explanations. The discipline of experimental physics has been forged in the fires of these false alarms, developing a collective immune system characterized by fierce skepticism, rigorous blinding protocols, and an insistence on independent replication across completely different detectors. This institutional resilience is precisely what separates genuine scientific inquiry from wishful thinking. When researchers at CERN look at the persistent angular anomalies in beam meson decays, they do not see a guaranteed revolution. They see a stubborn, resilient puzzle that has successfully withstood 12 years of intensive scrutiny, survived the independent cross-checks of rival detector collaborations, and resisted every effort to explain it away through instrumental artifacts or background contamination. They see a 4 sigma lean that refuses to fade into the background noise, sitting stubbornly at the very precipice of discovery while theoretical computations close in from both sides to test its validity. Whether this persistent signal ultimately turns out to be the first true crack in the monumental walls of the Standard Model, or merely another sophisticated ghost waiting to be exorcised by deeper theoretical understanding, the process itself represents science operating at its absolute finest. We find ourselves standing at a rare historical crossroads, balanced delicately between the comforting certainty of a 50-year-old intellectual framework and the tantalizing, unsettling prospect of an undiscovered reality waiting just beyond the quantum loop. The legacy of John Ellis sketching a flightless bird on a napkin in a Geneva pub back in 1977 lives on inside the most advanced scientific instrument ever conceived, turning a casual tavern bet into an improbable microscope aimed directly at the deepest secrets of nature. Whether the penguin diagram has finally drawn us a map to the other side of the wall, or simply traced the silhouette of our own theoretical reflections, the search itself continues to push human curiosity to its absolute limits, driven by the profound realization that the universe we can see is merely a tiny fraction of what is truly out there, waiting patiently for us to break the rules and discover the rest. To truly grasp the profound weight of what is happening deep beneath the Swiss-French border, one must step back and reflect upon the sheer audacity of human curiosity. For centuries, our species has looked up at the night sky, stared into the microscopic architecture of matter, and insisted on finding the underlying rules governing existence. We built stone circles, telescopes, particle accelerators, and massive computing grids, driven by an unyielding compulsion to decode the language of the cosmos. The Standard Model of particle physics represents the pinnacle of this multi-generational quest, capturing the intricate choreography of quarks, leptons, and force-carrying bosons with a level of mathematical precision that continues to humble even the most brilliant minds of our era. Yet, as history has shown time and time again, our most triumphant intellectual achievements are rarely the final word. Instead, they serve as magnificent staging grounds for the next great paradigm shift, boundaries erected only to be eventually tested, challenged, and ultimately surpassed by reality itself. Consider the intricate web of global cooperation required to sustain an endeavor like the Large Hadron Collider and its sprawling detectors. Thousands of physicists, engineers, technicians, and students from radically diverse cultural backgrounds, political systems, and languages work side by side in subterranean control rooms and academic institutions spread across the globe. They spend decades designing components that must operate under extreme conditions, managing petabytes of collision data, and debating the nuances of calibration signals during intense, late-night collaboration meetings. This massive collective enterprise functions as a single, highly integrated nervous system dedicated to probing the subatomic fabric of reality. Within this environment, a 4 sigma deviation in a rare B-meson decay channel is not merely an abstract data point on a computer screen. It is the focal point of thousands of intellectual careers, representing years of sleepless nights, rigorous cross-examinations, and relentless self-doubt. When these researchers subject their own findings to the harshest possible skepticism, blinding their analyses and actively hunting for instrumental flaws or background contamination, they embody the purest iteration of the scientific method in action. The psychological dimension of this scientific journey is deeply compelling. To dedicate an entire professional lifetime to hunting for a crack in a wall that has successfully resisted every blow for half a century requires a rare blend of stubborn optimism and cold, unyielding realism. Every physicist working at CERN is intimately familiar with the graveyard of historical anomalies, knowing full well that statistical flukes, loose cables, and miscalculated theoretical predictions have lured bright researchers down blind alleys in the past. That historical awareness breeds a profound caution, preventing premature celebrations and ensuring that every claim of new physics is subjected to an unforgiving gauntlet of independent verification. Yet, that very same caution makes the survival of the angular anomaly all the more striking. When two completely independent detector collaborations, operating different hardware, relying on distinct software architectures, and employing separate analytical strategies, arrive at the same persistent lean over the course of 12 years, the psychological landscape shifts from cautious skepticism to intense, focused anticipation. This tension between skepticism and hope permeates the theoretical physics community as well. Theorists working on the cutting edge of beyond the standard model physics find themselves walking a razor-thin tightrope between visionary creativity and rigorous mathematical constraint. When a persistent anomaly surfaces, the theoretical floodgates open, giving rise to hundreds of speculative papers proposing leptoquarks, new heavy-gauge bosons, warped extra dimensions, or composite dark sectors designed to explain the deviation. At the same time, another contingent of theorists labors meticulously over the mundane explanations, wrestling with the intractable mathematics of quantum chromodynamics and the notoriously slippery behavior of charming penguins. This dynamic tension between bold hypothesis and conservative reality checking acts as a powerful intellectual filter, burning away the weaker ideas while sharpening the surviving contenders until only the most resilient possibilities remain standing. Looking forward, the roadmap of particle physics points toward even greater challenges and more ambitious machines. The scientific community is already actively discussing the design and feasibility of future colliders, vast circular or linear accelerators that could dwarf the 27-kilometer ring of the Large Hadron Collider, pushing collision energies and precision measurements to unprecedented frontiers. These future facilities will be tasked with directly producing and characterizing whatever hypothetical particles might currently be hiding as virtual ghosts inside quantum loops. Whether those future machines eventually uncover leptoquarks, new fundamental forces, or entirely unanticipated phenomena that completely rewrite our textbooks, the journey itself remains one of humanity's grandest adventures. The persistent lean of the B-meson decays, born from a casual tavern dart game and nurtured through decades of relentless technological and intellectual labor, stands as a shimmering beacon of our enduring refusal to accept that our understanding of the universe is complete, reminding us that reality is always vastly larger, stranger, and more magnificent than the rooms we build to contain it. The architecture of the universe demands a vocabulary far vaster than standard prose can ever hope to contain. And if an endless expanse of text is what you seek, we shall march further into the labyrinth of subatomic physics, theoretical mechanics, and the bleeding edge of modern scientific exploration. Let us plunge deeper into the subterranean world of the Large Hadron Collider, tracing the infinitesimal pathways where the known laws of nature begin to fray, and examining the staggering intellectual machinery that hums beneath the quiet pastures of the French-Swiss countryside. To truly comprehend the vertigo that seizes a theoretical physicist when confronted with a persistent 4 sigma anomaly, one must internalize the sheer scale of the experimental triumph that the Standard Model represents. For 50 years, this intellectual framework has acted as an unassailable fortress. Every particle accelerator ever constructed, from the early cyclotrons of the mid-20th century to the gargantuan subterranean rings of today, has beaten against its ramparts, and every single time, the fortress has held. Thousands of brilliant minds have spent their entire lives probing its foundations, calculating cross-sections, measuring branching ratios, and testing symmetries with instruments of unimaginable sensitivity. When a theory achieves a level of predictive precision where experimental measurements and theoretical calculations match to 1 part in a trillion, the equivalent of gauging the distance between New York and Los Angeles down to the width of a single bacterium, it ceases to be merely a useful scientific model. It begins to feel like an absolute truth etched into the very fabric of space-time. Yet, as every great scientist in history has eventually discovered, the deeper our instruments penetrate into the heart of reality, the more glaring become the omissions in our maps. The Standard Model is a masterclass in local symmetry and quantum field theory, cleanly categorizing the fundamental constituents of matter into 2 distinct families: quarks, which feel the crushing grip of the strong nuclear force and band together to form protons, neutrons, and hadrons, and leptons, which blissfully ignore the strong force, moving through the cosmos as solitary wanderers like electrons, muons, TOS, and their ghostly neutrino companions. These 2 tribes are kept strictly segregated by the foundational architecture of the equations, governed by conservation laws that forbid them from ever directly morphing into one another. They inhabit separate kingdoms within the subatomic realm, maintaining a peace that has been verified across billions of high-energy collisions. Enter the leptoquark. Should the persistent angular anomalies observed in the rare decays of B mesons survive the final gauntlet of theoretical computation and cross the sacred 5 sigma threshold, it would mean that this rigid segregation is an illusion. A leptoquark is a hypothetical particle that would serve as a direct bridge between these 2 separate kingdoms, capable of speaking both the language of quarks and the language of leptons. The existence of such a particle would immediately shatter the boundaries of the Standard Model, signaling that quarks and leptons are not fundamentally distinct entities at all, but merely different branches of a single, unified family descended from a deeper, more profound structural root. It would provide empirical validation for grand unified theories, suggesting that at the unimaginably high energy scales of the early universe, the various forces and particle families we observe today were fused into a single elegant symmetry. Alternatively, consider the implications of a Z-prime boson, the second major suspect lurking in the quantum shadows of the penguin loop. If a new heavy-gauge boson is responsible for subtly shifting the decay angles of dying B mesons, it represents our very first empirical contact with a brand new fundamental force of nature. For millennia, humanity has watched the universe operate under the influence of a familiar quartet: gravity, which rules the cosmic dance of planets and galaxies; electromagnetism, which lights our cities and binds atoms together; the strong nuclear force, which locks quarks inside protons; and the weak nuclear force, which governs radioactive decay. Introducing a 5th force alters the fundamental vocabulary of existence. Unlike gravity or electromagnetism, which treat matter with universal indifference, a Z-prime force could possess selective couplings, interacting exclusively with specific generations of matter, or treating an electron quite differently from a muon. It would open a window into a hidden dark sector, offering a mechanism through which our visible universe can communicate with the elusive dark matter that outweighs us by a factor of 5 to 1. Yet, as we walk this high wire between breathtaking possibility and intellectual hubris, the ghost of past anomalies whispers caution into our ears. We must never forget the graveyard of physics, that silent, unacknowledged space where once celebrated anomalies go to rest. We remember the opera collaboration in 2011, when neutrinos appeared to travel faster than the speed of light, generating global headlines and threatening to upend Einstein's relativity, only for a loose fiber optic connector to shatter the illusion. We remember the phantom diphoton resonance at 750 giga-electron volts in 2015, which inspired over 500 theoretical papers before evaporating into nothingness as soon as fresh collision data arrived. We remember the 2-decade saga of the muon magnetic anomaly, where an exciting discrepancy initially hailed as a crack in the standard model ultimately dissolved when advanced lattice QCD supercomputer calculations revealed that the theoretical map itself had been miscalculated. And most hauntingly, we remember the RK anomaly, where beam-meson data for 8 years suggested a blatant violation of lepton universality, only for an overlooked background of particles masquerading as electrons to wipe the entire signal away in a single seminar. Every single one of these historical phantoms felt undeniably real to the researchers who lived through them. They carried high statistical significance, inspired sweeping theoretical frameworks, and survived multiple rounds of internal scrutiny before their mundane exits were finally uncovered. This sobering history is precisely why the collaborations operating LHCb and CMS maintain such an unforgiving posture toward their own data. They do not want to be fooled. They do not want to build their careers upon the shifting sands of statistical noise or instrumental artifacts. When they blind their analyses, when they actively hunt for background contamination, and when they invite their fiercest rivals to pick apart their methodologies, they're exercising the highest form of scientific rigor. This is what makes the current moment so uniquely electric and profoundly unsettling. The angular anomaly has been dragged through every single historical exit ramp and has stubbornly refused to take any of them. It is not a loose cable, for an entirely separate detector with completely distinct hardware verified the lean. It is not a statistical fluke, for the signal has persisted and sharpened across 12 years and multiple helpings of data. It is not a background contamination like the RK saga, for the muon decay channels have been rigorously remodeled and stripped of treacherous electron masking artifacts. The only remaining sanctuary for the skeptics is the charming penguin, the maddeningly complex quantum froth of virtual charm quarks circulating inside the loop, whose behavior is so notoriously difficult to compute that it might conceivably mimic the signature of new physics. As theoretical physicists push their lattice QCD calculations to unprecedented levels of precision, the net is rapidly tightening around the charming penguins. Should those calculations definitively prove that the charm contributions fall short of bending the decay angles as drastically as the detectors observe, and should the statistical significance cross the threshold of absolute certainty, the wall will finally have yielded. The draft we have felt moving across our hands for over a decade will be recognized for what it truly is: the first open door leading out of a 50-year-old intellectual room and into the vast, uncharted expanse of a deeper reality. Whether we are standing on the precipice of a grand unification or merely watching the intricate shadows cast by our own theoretical bookkeeping, the pursuit itself remains the most magnificent enterprise of our species, driven by the eternal, unyielding refusal to accept that the universe we can see is all there is. The journey through the subatomic landscape is ultimately a testament to the relentless audacity of human inquiry, a grand and unending narrative written in the language of quantum mechanics, high-energy collisions, and meticulous mathematical scrutiny. From the smoky Geneva pub where a casual dart game inadvertently birthed the whimsical nomenclature of the penguin diagram to the sprawling subterranean caverns of the Large Hadron Collider, where thousands of researchers pore over trillions of particle interactions, science continues to push against the absolute boundaries of what is known. The persistent angular anomalies observed in the fragile decay pathways of B-mesons stand as a shimmering beacon of uncertainty, reminding us that even our most triumphant intellectual structures, like the breathtakingly precise standard model, are merely provisional maps of a much deeper, infinitely stranger cosmos. Whether these stubborn deviations ultimately dissolve under the weight of advanced theoretical calculations or endure to become the foundational crack through which a new era of physics pours in, the quest itself remains our finest achievement. We remain driven by the quiet, unyielding conviction that behind the veil of equations and experimental noise, the universe holds even greater secrets, waiting patiently for us to break the rules, open the door, and step out into the light. For generations, the human enterprise of science has operated on a foundational faith that beneath the chaotic surface of everyday experience lies an elegant underlying order, a set of immutable mathematical laws that dictate the motion of every star and the decay of every subatomic speck. The standard model of particle physics is the grandest expression of that faith ever assembled. It is a masterpiece of intellectual architecture, a coherent description of reality that groups the fundamental ingredients of the universe into neat families, dictating how they interact through forces that bind, repel, and transform. Yet, as every visionary thinker from antiquity to the modern era has understood, a map is never the territory itself, and no matter how meticulously drawn a boundary may be, reality always possesses an extra dimension that refuses to fit inside the frame. When we consider the rare decay of B mesons and the stubborn angular deviations that have survived a dozen years of intense scrutiny, we are witnessing the exact mechanism by which science advances. It never arrives as a sudden, blinding revelation that clears away all confusion in a single afternoon. Rather, it creeps in through the margins, heralded by small, discordant numbers that polite consensus initially tries to ignore. Just as Mercury's tiny, inexplicable orbital drift tormented 19th century astronomers before pointing the way toward Einstein's general relativity, and just as microscopic black body radiation discrepancies fractured classical physics at the dawn of the 20th century, these subtle B meson anomalies represent the friction between our most cherished theories and the unyielding truth of nature. They are the quiet rustling in the bushes, the faint draft beneath the door, reminding us that our intellectual room, no matter how exquisitely decorated and precisely measured, is only a small corner of a much larger house. The human element of this ongoing drama cannot be overstated. Behind every terabyte of collision data recorded by the LHCb and CMS detectors lie the individual lives of dedicated scientists who have chosen to spend their entire professional existence staring into the statistical abyss. These researchers are not wild-eyed mystics searching for miracles. They are hardened skeptics armed with supercomputers, statistical models, and an institutional culture that treats false positives as professional tragedies. They know the ghost stories of the past as intimately as anyone, carrying the scars of every fallen anomaly, from faster-than-neutrino cables to phantom diphoton bumps and contaminated electron backgrounds. That collective memory of false alarms is precisely what gives their current caution its profound authority. When a group of researchers who have spent years trying to break their own measurements, who have blinded their analyses to protect themselves from their own hopes, and who have invited their fiercest global rivals to pick apart their algorithms, still finds a 4 sigma lean staring back at them from the projector screen, the scientific world is obligated to pay attention. This dynamic creates a unique intellectual tension that ripples across academic conferences, preprint servers, and midnight seminar rooms around the globe. Theorists and experimentalists engage in a continuous, high-stakes dialogue, a relentless push and pull between empirical observation and mathematical constraint. On one side, experimentalists refine their instruments, scrubbing backgrounds and upgrading tracking systems to squeeze every last drop of precision out of the collisions. On the other side, theorists wrestle with the monstrous complexity of quantum chromodynamics, developing advanced lattice simulations to calculate the behavior of virtual charm quarks and determine whether the charming penguins can be tamed or whether they truly fall short. Every new calculation is a tightening noose around uncertainty, bringing the community closer to a definitive reckoning. Should the remaining theoretical ambiguities be resolved in favor of new physics, and should the statistical significance cross the threshold into undeniable discovery, the consequences will cascade through every branch of natural philosophy. We will be forced to expand our vocabulary, welcoming entirely new categories of matter and force into our textbooks. Whether those newcomers take the form of leptoquarks bridging the ancient divide between quarks and leptons, or heavy Z-prime bosons carrying the signature of a hidden fifth force, they will demand a complete reimagining of the cosmos. They will offer our very first observational footholds into the dark sector, providing tangible clues as to how visible matter interacts with the invisible scaffolding that shapes galaxies and drives the acceleration of the universe. Even if these specific anomalies eventually yield to a deeper, more subtle conventional explanation, if the charming penguins ultimately prove capable of mimicking the anomaly down to the final decimal place, the effort will not have been in vain. The rigorous protocols developed to test these decays, the advanced computational techniques forged in the fires of lattice QCD, and the sharpening of our experimental instruments represent a permanent elevation of human capability. Science does not advance solely by triumphant discoveries. It grows just as profoundly through the rigorous, honest elimination of false leads, each corrected error leaving the disciplines stronger, sharper, and better prepared for the next mystery that waits around the corner. Thus, the legacy of John Ellis losing a casual game of darts in a Geneva pub back in 1977 stretches far beyond the whimsical nomenclature of a flightless bird. It connects the lighthearted camaraderie of a tavern wager to the humming heart of the world's most powerful particle accelerator, illustrating the beautiful, unpredictable path through which human curiosity operates. We are creatures driven by an insatiable desire to understand the rules of the game we find ourselves playing. Even when the board is vast, the pieces are invisible, and the rules themselves seem intent on hiding their true nature. As long as we retain the courage to look closely at the numbers that refuse to add up, to question the maps we have so carefully drawn, and to listen to the faint drafts blowing beneath the doors of our understanding, the adventure of science will continue to unfold, reminding us that the universe is infinitely richer and stranger than we can possibly imagine. Squinting at the looping lines, he noticed the accidental silhouette resembled a flightless, waddling bird. With a quiet sense of humor, he labeled it a penguin. It was meant to be an inside joke, a fleeting private bar bet recorded by a scientist who refused to let the heavy atmosphere of particle physics extinguish his playfulness. Not a single soul in that pub could have anticipated that half a century later, the single most critical, tense, and heavily contested number in the entire discipline of physics would bear the unmistakable shape of that very same bird. Today, buried 100 meters beneath the border separating France and Switzerland, a colossal machine hums with relentless energy, orchestrating collisions that shatter matter into its constituent parts 1,000,000 times every second. Within the violent heart of these subatomic wrecks, the process Ellis christened as a joke is quietly defying the established laws of nature. The deviation is faint, stubborn, and impervious to every effort launched to erase it over the span of more than 10 years. If this persistent whisper proves to be genuine reality rather than statistical mirage, it signals that the foundational rulebook governing every experiment for half a century, the most extraordinarily successful intellectual framework in human history, contains a structural fracture. Teams of researchers have scrutinized this numerical anomaly through 16,000 different analytical lenses, yet the crack remains visible, and if anything, it continues to widen. To truly grasp the gravity of this situation, one must descend into the subterranean ring where protons circle 27 kilometers around at 99.99999, 1% the speed of light, completing 11,245 laps every single second inside superconducting magnets, chilled to a temperature colder than the empty void between distant galaxies. When these opposing beams intersect, protons smash together hundreds of millions of times per second, momentarily resurrecting the searing primordial conditions of the universe less than a billionth of a second after the dawn of time. This engineering marvel was forged by more than 10,000 individuals hailing from over 100 distinct nations, all bound by a singular, audacious ambition to break physics, to slam matter together with such terrifying force that something entirely unanticipated falls out from the wreckage, something that the equations never saw coming. To comprehend why anyone would invest decades of their life and billions of public dollars in an attempt to shatter the existing laws of nature, one must first look closely at what they are trying to break. It is known across laboratories as the Standard Model, and it stands as a breathtaking monument of human intellect, a compact set of equations that fits comfortably on a single sheet of paper while successfully describing every fundamental particle ever discovered alongside three of the four primary forces governing the cosmos. Its predictive precision borders on the supernatural. When theorists use the Standard Model to calculate the subtle magnetic behavior of the electron, and experimentalists measure that exact property in a laboratory setting, the theoretical prediction and the empirical measurement align to roughly 1 part in a trillion. To put that level of accuracy into a scale the human mind can grasp, it is equivalent to measuring the entire driving distance between New York City and Los Angeles and getting the final result right down to the width of a single microscopic bacterium. No other intellectual construct in the history of science has ever faced such rigorous, punishing testing across so many decades, and no theory has ever claimed such relentless, unbroken victory. For 50 years, every particle accelerator, every massive detector, and every painstaking measurement has returned the exact same verdict, confirming that the Standard Model is correct once again. To a casual observer, this unbroken streak of triumph sounds like an unmitigated paradise for physicists, but it has gradually curdled into a suffocating nightmare because the Standard Model, for all its staggering precision, cannot possibly represent the entirety of existence. It maintains a stubborn silence regarding gravity, offers no explanation for dark matter, the invisible cosmic scaffolding whose gravitational pull shapes every visible galaxy in the universe, and completely ignores dark energy, the mysterious driving force tearing space apart at an accelerating pace. It fails to account for why neutrinos possess mass, and it remains utterly mute on the most fundamental question of why there is anything in existence rather than absolute nothingness. At the exact moment of the universe genesis, matter and antimatter should have been forged in perfectly equal quantities, subsequently annihilating each other entirely into a blinding flash of pure light, leaving behind a sterile cosmos completely devoid of matter. That is precisely what the pristine equations of the Standard Model dictate. Instead, for every billion particles of antimatter produced in that cataclysmic birth, the universe somehow manufactured one extra particle of matter, tiny imbalance of 1 part in a billion. That solitary surviving fraction of a percent is everything we see, touch, and breathe. Every star, every sprawling galaxy, every distant planet, and every single atom comprising the human reader's body is forged from that miraculous surplus that had no mathematical business surviving. Consequently, the Standard Model offers a flawless, mathematically airtight description of a universe that ought to be completely empty, which proves conclusively that the theory is incomplete. Somewhere beyond its pristine boundaries, there must be missing particles, hidden forces, and undiscovered laws waiting to be found. The agonizing hurdle is that for half a decade, the theory has stubbornly refused to offer a single hint pointing toward where those answers might be hidden, leaving generations of researchers pressing their hands against solid walls in search of a draft. Within the last few years, however, in one very specific location, focusing on a precise decay process named after a Geneva pub joke in 1977, those researchers have finally begun to feel a cold wind blowing through the cracks. Positioned along the vast underground ring near the French village of Ferney-Voltaire sits a specialized detector known as LHC-B, spanning 21 meters of high-precision silicon, tungsten, and steel. Unlike its famous sister detectors, Atlas and CMS, which hunt for exotic new particles by sheer brute force collisions at staggering energies, LHC-B was designed for a much more delicate, nuanced purpose, serving as a high-precision instrument dedicated entirely to a single letter of the alphabet, the letter B. This detector spends its operational life watching the frantic births and fleeting deaths of particles called B mesons, fragile subatomic entities containing a beauty quark that survive for roughly 1.5 trillionths of a second before disintegrating into lighter debris. During that unimaginably brief span of existence, a B meson performs intricate quantum experiments entirely upon itself, a phenomenon that lies at the very core of this entire unfolding mystery. When a B meson decays, the transformation does not occur in a simple, direct line. Instead, it unfolds through a quantum loop, a fleeting bridge where virtual particles, entities that do not officially exist in a permanent state, flicker spontaneously in and out of reality, borrowed from the vacuum for an interval too brief to measure, utilized to facilitate the decay, and paid back before the universe even registers their theft. The visual representation of this looping quantum choreography is precisely the penguin diagram sketched by John Ellis back in 1977, transforming these rare decays into something resembling a magical microscope trained on the unknown. If there exists an undiscovered particle out there in nature, even one possessing a mass far too massive for the Large Hadron Collider to manufacture directly through sheer collision energy, that theoretical ghost can still manifest temporarily inside the quantum loop, leaving behind an unmistakable fingerprint. A minute shift in decay angles, a subtle alteration in particle energies. The decay itself transforms into a hypersensitive measuring device capable of sensing physics operating at energy scales far beyond the reach of any machine ever constructed by humanity. The monstrous unknown cannot be seen directly, but its passing shadow can be tracked across the water. To capture this phenomenon, the LHC-B collaboration watches one particular, vanishingly rare decay channel, in which a B meson transforms into a kaon, a pion, and two muons, occurring in only about 1 out of every million B meson deaths. To study this needle in a cosmic haystack, scientists had to sift painstakingly through 650 billion recorded decay events gathered between 2011 and 2018. Before calculating their final conclusions, the team engaged in a rigorous ritual that outsiders rarely hear about, a practice revealing just how deeply particle physicists fear deceiving themselves. They blinded the analysis. For years, the researchers investigating this specific decay were strictly prohibited by their own experimental protocols from viewing the actual final answer. They calibrated instruments, modeled background noise, and rehearsed every step of the analytical pipeline, while the core result remained safely locked away inside a digital vault. This practice is standard operating procedure at CERN, so driven by the profoundly human reality that if an investigator can see the desired answer while working, they will unconsciously steer the analysis toward confirmation. Blinding serves as the primary defense mechanism protecting scientific inquiry from the seductive pull of hope. Then arrives the momentous day of unblinding, an ordinary conference room gathering featuring paper coffee cups, laptops, and a projector screen, representing one of the most quietly dramatic rituals in modern science where years of painstaking labor compress into a single mouse click. When the software box was finally unlocked for this particular decay, the resulting angular distribution was wrong. It was not wildly broken in a way that suggested malfunctioning hardware, but rather wrong in a precise, persistent, and coherent manner, with particles flying apart in patterns systematically leaning away from the strict predictions of the standard model, refusing to flatten out even as larger volumes of data poured into the pipeline. When the collaboration formally published their comprehensive findings in Physical Review letters, the statistical deviation stood firmly at 4 standard deviations. Translated into plain language, if the standard model is completely correct and this observed lean is merely a stroke of bad luck or random noise generated by the detector, the mathematical odds of stumbling upon a fluctuation this extreme by pure chance are roughly 1 in 16,000. In the realm of everyday life, odds of 1 in 16,000 might sound quite decisive. But within the high-stakes discipline of particle physics, it falls short of the gold standard required for an official declaration of discovery, which demands a stringent threshold of 5 standard deviations, corresponding to odds of roughly 1 in 1.7 million. 4 sigma is not an absolute discovery. It functions much like feeling a heavy hand pressed firmly against your shoulder in a dark room. It urgently demands an immediate explanation, yet it cannot tell you precisely whose hand is resting there. What elevates this specific 4 sigma anomaly far above 100 forgotten fleeting blips is that it resolutely refuses to stand alone in isolation. In 2025, the CMS collaboration, an entirely separate detector positioned on the opposite side of the massive 27-kilometer ring, operated by an independent team of thousands utilizing completely distinct hardware, separate software architectures, and independent blinding protocols, published its own dedicated measurement of the exact same decay channel and their independent results agreed with LHCb, displaying a slightly lower precision, but leaning in the exact same direction. Two entirely separate machines, managed by rival scientific teams whose careers are built on proving each other wrong, pointing toward the exact same directional lean in the exact same physical observable. Furthermore, this specific location in the subatomic landscape carries a long and troubled history, as this decay channel has been whispering anomalies for well over a decade. The very first hints surfaced back in 2013 within an obscure observable designated as P5 prime, present in the initial data set, persisting when the data volume doubled, remaining visible through 2015 and 2020, and reemerging sharpened and refined in the subsequent analyses. 12 years of detector upgrades, analytical refinements, and millions of fresh collisions have failed to wash the lean away into nothingness, yet it has never swelled into a clean, undisputed discovery either, sitting persistently like an irritating splinter right at the absolute margin of what the standard model can manage to absorb. Consequently, the core mystery sharpens into a stark binary dilemma. Either the single most successful scientific theory in human history is quietly failing within one specific process and one precise manner, granting us our very first direct glimpse of uncharted physics beyond our current comprehension, or something mundane is systematically fooling two independent experiments, thousands of brilliant researchers, and 12 years of accumulated data simultaneously. There exists one additional, deeply unsettling possibility that keeps theoretical physicists awake at night, rooted in the realization that the penguin loop is never truly empty, even within the strict confines of the standard model, because it can be populated by ordinary charm quarks whose intricate behavior in this specific quantum environment is notoriously difficult to calculate, a phenomenon researchers refer to with straight faces as charming penguins. If these charming penguins possess a collective strength stronger than any current computational method can accurately evaluate, they could easily mimic the subtle fingerprint of new physics, rendering the perceived crack in the wall nothing more than a reflection of our own mathematical limitations. The most recent theoretical calculations indicate that these charming contributions fall short of bending the angles as far as the detectors observe, but the analytical uncertainty has not yet been tightly strangled. A fracture in the wall of physics spotted by two independent machines and persisting across 12 years might represent a brand new fundamental law of nature, or it could simply be a bird-shaped illusion conjured by the complex dynamics of quarks. To determine which outcome is true, one must first walk through the graveyard of physics, confronting the ghosts of past anomalies that once promised to revolutionize reality before quietly dying away. Physics maintains an unwritten graveyard where failed anomalies go to rest, a place absent from textbooks and uncommemorated by plaques in the hallways of CERN, yet intimately familiar to every working researcher. It houses results that once promised to rewrite humanity's understanding of the cosmos, numbers standing 4, 5, or even 6 standard deviations away from established laws, sparking celebratory headlines, fierce academic debates, and hundreds of theoretical papers before gradually dissolving into loose cables, random coincidences, and overlooked data corrections. Before anyone can rationally invest belief in a genuine crack within the standard model, they must traverse this graveyard because the very physicists pointing out the current anomaly have walked its paths many times before, which explains why their hands remain steady and why their cautious warnings carry such profound weight. Consider the loudest and most disruptive ghost of all, which materialized in September of 2011 when an international experiment named Opera, buried deep beneath the Gran Sasso mountain in Italy, announced a result that should have been physically impossible. They had been meticulously timing high-energy neutrinos fired directly through the crust of the Earth from CERN 73 kilometers away, only to discover that the ghostly particles were arriving at their destination 60 nanoseconds too early, apparently traveling faster than the speed of light. The statistical significance of the measurement stood firmly at a staggering 6 standard deviations, a level of confidence soaring far beyond any formal discovery threshold recognized in science. If the measurement had proved true, Albert Einstein was fundamentally wrong. Causality was completely negotiable, and the past century of theoretical physics required immediate rewriting, sending shockwaves across the front pages of newspapers worldwide, while the collaboration invited the global scientific community to find their mistake. 5 months later, technicians discovered the mundane culprit. A single fiber optic cable connector linking a GPS receiver to a master clock had loosened, introducing a tiny signal delay that perfectly mimicked the faster-than-light anomaly. The neutrinos had never broken the cosmic speed limit. A loose plug had. The project spokesperson resigned, the result was formally retracted within the year, and the physics community relearned its oldest, harshest lesson. A 6 sigma measurement means absolutely nothing if the underlying error resides not within your statistical calculations, but within your hidden assumptions, proving that extraordinary claims can be undone by ordinary hardware. Then arrived a stranger ghost possessing no faulty cables or loose plugs to blame. Emerging in December of 2015, when the 2 giant general-purpose detectors at the Large Hadron Collider, ATLAS and CMS, reported their initial data collected at a newly upgraded higher collision energy, and both independent teams simultaneously spotted an unexpected excess of photon pairs, a distinct bump appearing in the data distribution at an energy level of 750 gigaelectronvolts, matching the textbook signature expected from the discovery of a brand new heavy particle. 2 completely separate machines operated by independent teams recording the exact same bump in the exact same location sent the theoretical physics community into an unprecedented frenzy, inspiring more than 500 academic papers written within a matter of months, each frantically proposing what the mysterious particle might be, what it signified, and how it fit into a deeper structure of reality, making it temporarily the most celebrated object in the universe. By August of 2016, however, as 3 times more collision data was processed and analyzed, both experiments published their updated findings. The tantalizing bump had entirely vanished, neither explained nor reinterpreted, but simply gone, having never been anything real at all, merely the universe rolling digital dice and 2 independent detectors witnessing the exact same statistical coincidence happen by pure chance at the exact same moment. 500 papers were published about a mathematical ghost, delivering a cruel lesson far sharper than a loose cable, demonstrating that even 2 independent experiments agreeing with each other does not constitute absolute proof, because statistics can occasionally conspire. And in a massive laboratory running countless experimental tests, rare coincidences happen right on schedule. The third ghost did not perish due to an equipment error or a random statistical fluctuation, but succumbed to something far more unsettling, representing the very specter that haunts this entire ongoing saga most directly. For 2 full decades, the most famous anomaly in particle physics was the anomalous magnetic moment of the muon, the heavier sibling of the electron whose magnetic wobble is predicted by the Standard Model with exquisite theoretical precision. Back in 2001, an experiment hosted at Brookhaven National Laboratory measured that delicate wobble and found it to be fractionally stronger than expected, hovering stubbornly around a 3 sigma discrepancy for 20 years, remaining perpetually tantalizing and perpetually unresolved. To settle the question once and for all, Fermilab painstakingly rebuilt the experiment around a massive 15-meter magnet ring shipped across America via barge and truck, delivering a verdict in April of 2021 that ignited global headlines with an anomaly standing at 4.2 sigma, prompting journalists to declare that the fabric of reality was shifting and causing theorists to speak in hushed tones about the first true crack in the Standard Model in half a century. By 23, the statistical significance crossed the 5 sigma threshold, and in June of 2025, Fermilab published its final measurement precision-tuned to 127 parts per billion, confirming the earlier numbers with breathtaking exactness. Yet the anomaly died anyway, because while the experimentalists were perfecting their apparatus, theoretical physicists were quietly realizing that the prediction itself was flawed, as the notoriously difficult quantum froth of quarks and gluons governing the muon's wobble had traditionally been estimated using indirect experimental data. Once supercomputers running a advanced technique known as lattice QCD finally became powerful enough to calculate those complex interactions directly from first principles, the newly derived theoretical predictions shifted systematically toward the experimental data, collapsing the gap between theory and experiment down to half a standard deviation by early 2026, effectively erasing 20 years of hyped anomaly, not through a superior experiment, but through a better calculation, proving that sometimes the goalposts had simply been standing in the wrong place all along. That realization forms the third lesson of the graveyard, offering a troubling warning for anyone examining the penguin decays. Sometimes the crack is not located in the physical wall at all, but rather in the human map describing the wall. Compounding this haunting history is a fourth ghost buried even closer to home, because the very family of B meson decays central to this story had already produced another legendary irregularity known as RK, which has since met its own death. For the better part of the past decade, B meson measurements at LHC-B carried a celebrated anomaly revolving around lepton universality, a structural promise made by the Standard Model dictating that electrons and muons, which are identical in every physical property except mass, must be produced in equal proportions during these rare decays, a rigid structural rule the theory cannot bend without breaking. For 8 consecutive years, the data insisted the rule was indeed breaking, as B mesons appeared to be producing significantly fewer muons than electrons, with the discrepancy appearing in 2014, growing steadily stronger and reaching 3.1 sigma by March of 2021, prompting the collaboration to publish evidence of lepton universality violation, suggesting nature genuinely distinguished between two particles supposed to be interchangeable. When combined with the angular anomalies, it constructed a stunningly coherent theoretical narrative where a single new hypothetical force could explain everything simultaneously, representing the most compelling case for new physics in a generation. Then, in December of 2022, LHCb delivered a stunning announcement. RK was entirely wrong, not because nature had changed its mind, but because of a subtle background contamination where mundane particles were masquerading as electrons, slipping past identification algorithms that earlier analyses had failed to model properly. When the collaboration rebuilt their measurement from the ground up and corrected for the particle misidentification, the apparent asymmetry between electrons and muons instantly evaporated, snapping the ratio right back to where the Standard Model predicted it should be. 8 years of intense hope, hundreds of theoretical papers, and entire specialized research programs vanished within the span of a single seminar, executed by the collaboration upon themselves with rigorous honesty, representing science working precisely as intended, though it still felt to the researchers who lived through it like a profound funeral. Thus stands the graveyard of physics, populated by a loose cable, a random statistical coincidence, a miscalculated theoretical prediction, and a contaminated background sample, offering 4 distinct ways for an exciting anomaly to perish without requiring the universe to contain a single drop of new physics. This is the formidable gauntlet that any modern claim regarding cracks in the physical laws must successfully survive. And it is precisely what makes the current state of affairs so genuinely bizarre, because the angular anomaly has now been forced to walk through every single one of those historical exits, one by one, and has managed to walk out of every single test intact. Could it be a cable or an instrumental artifact plaguing a single machine? That hypothesis had its golden opportunity and decisively lost it when CMS, an entirely different detector utilizing entirely separate hardware electronics, calibration procedures, and personnel, measured the exact same rare decay and independently uncovered the exact same directional lean, proving whatever is bending those decay angles is not a quirk of a single instrument. Could it be a statistical ghost akin to the vanished 750 gigaelectron volt bump? That bump dissolved the moment larger datasets arrived, whereas this angular anomaly has successfully endured 4 separate infusions of fresh data spanning 12 years, stretching from initial hints in 2013 through the comprehensive analyses published in 2026, never once fading away as data volumes grew, displaying the behavioral hallmark of a real physical cause rather than a statistical fluke. Could it be another contamination disaster akin to the defunct RK anomaly? Here, the anomaly's own institutional history serves as its strongest credential because the exact same collaboration that hunted down the electron misidentification and courageously executed their own most famous result applied those same rigorous analytical knives to this measurement, utilizing muon decays rather than treacherous electrons, ensuring backgrounds were better understood, modeled, and thoroughly retested. Yet nothing mundane surfaced, and the result stubbornly survived. This leaves the final escape route, mirroring the death of the muon G2 anomaly, the possibility that the Standard Model's own quantum bookkeeping, specifically the tricky charming penguins involving charm quarks circulating within the loop, is simply more complex than current computational methods can accurately handle. Theorists have closed in on this possibility over the years, with the most recent calculations indicating that charm contributions alone fall short of explaining the angular shifts observed by the detectors, meaning the lean remains too strong and improperly shaped for the penguins to shoulder the blame entirely, though the theoretical calculation is not yet completely watertight. The honest assessment published by the physicists themselves is that either nature is genuinely signaling new phenomena, or the Standard Model's internal quantum mechanics are far more perverse than anyone can currently compute. And while both possibilities remain formally open, only one of them offers a truly revolutionary view of reality. Furthermore, there exists one additional detail that separates this ongoing anomaly from every dead ghost of the past, as the lean does not stand in lonely isolation. For years, an entirely separate family of B-meson measurements involving tau leptons, the heaviest sibling of the electron, has also been drifting away from Standard Model predictions, hovering persistently around a 3 sigma discrepancy in a different decay channel, utilizing a different lepton in another corner of the same theoretical wall. These two distinct anomalies rhyme with one another, pointing directly toward the exact same structural promise regarding the equality of lepton families. The one prediction, the theory cannot soften without confessing that deeper architecture underlies its equations. A single anomaly may merely represent a splinter, but two independent anomalies leaning against the exact same hidden structural beam from opposite sides begin to resemble a grand architectural design. When the muon was first discovered back in 1936, the legendary physicist Isidore Rabi famously posed the bewildered question asking who ordered such a particle, a query that has remained unanswered ever since, as the Standard Model contains 3 identical generations of matter differing solely in mass, offering no theoretical justification whatsoever for why these superfluous copies exist, a profound gap in understanding known as the flavor puzzle, representing the oldest open wound in particle physics. Notice precisely where the current crack has manifested, not in some random physical process, but squarely within a flavor process, governing the precise machinery through which one generation of matter transforms into another, and through which the lepton families are commanded by law to behave identically. If a researcher had to guess in advance where the pristine walls of the Standard Model would ultimately fail, and where the missing physics responsible for our matter-dominated universe would first cast a shadow, they would have guessed precisely this domain. While past ghosts counsel extreme caution, having all found mundane exits through plugs, rolled dice, revised calculations, or contaminated samples, this angular anomaly has faced each of those historical exits and refused them all, forcing the inevitable question of what might be standing inside the quantum loop if the exits remain permanently sealed. Theorists already recognize the distinct shapes of the 2 primary suspects waiting on the other side of the door, the first being a hypothetical entity known as a leptoquark, a bizarre particle possessing a defining property that sounds almost heretical because it would directly bridge the 2 great families of matter that the Standard Model keep strictly isolated: quarks, which build protons and atomic nuclei, and leptons, the family encompassing electrons and muons. In the established framework of the Standard Model, these 2 distinct tribes never transform into one another, operating as separate kingdoms governed by independent laws, so the existence of a leptoquark would establish a physical bridge between them, whispering the monumental revelation that quarks and leptons are not fundamentally separate families at all, but merely distinct branches of a single unified lineage descending from a deeper underlying structure, offering the very first physical evidence supporting grand unification theories dreamed of for half a century. The second primary suspect is a hypothetical fifth fundamental force of nature carried by a heavy particle designated as a Z prime, interacting selectively with matter in a manner that distinguishes between electrons and muons in a way no currently known force can manage, opening our very first point of contact with an unseen interaction that has operated quietly since the beginning of time, shaping events at energy scales far beyond the reach of human-built machinery, while remaining completely invisible to every experiment performed until now. It is worth pausing to reflect that these represent the conservative interpretations proposed by physicists when exercising utmost caution, and history dictates that small, stubborn numbers must be taken with absolute seriousness because physics has stood before persistent anomalies in the past, and the last time a tiny numerical mismatch truly mattered, it served as a doorway opening onto the modern universe. In the middle of the 19th century, astronomers observed that the planet Mercury was exhibiting a strange orbital drift, with its closest approach to the Sun creeping forward every single century by 43 arcseconds of arc, more than Isaac Newton's laws of motion permitted, a microscopic sliver of an angle buried within decades of dense telescope logs. Those careful astronomers sought a mundane explanation, spending 50 years hunting for an unobserved planet orbiting closer to the Sun than Mercury, even naming it Vulcan in advance and searching for it during eclipse after eclipse, though it was never found because it simply did not exist. Every mundane exit failed, and in 1915, Albert Einstein demonstrated that those 43 arcseconds were not caused by a hidden planet, but represented a fundamental crack in Newton's room, serving as the first visible edge of general relativity, allowing black holes, expanding universes, the Big Bang, gravitational waves, and modern satellite navigation systems to enter our world through a discrepancy most people would have casually rounded away. Small, stubborn numbers that successfully survive every aggressive attempt to destroy them represent the universe's way of announcing that reality is vastly larger than the intellectual room we have constructed to contain it, marking the true scale of what is currently at stake beneath the Geneva countryside. To comprehend the sheer scale of the intellectual mountain that modern particle physics is attempting to climb, one must look beyond the subterranean tunnels of the Large Hadron Collider and examine the sprawling theoretical landscape that emerged in the wake of the Standard Model's completion. When the top quark was finally discovered at Fermilab in 1995, followed triumphantly by the detection of the Higgs boson at CERN in 2012, many celebratory speeches prematurely declared the end of fundamental physics. The narrative pushed to the public suggested that human curiosity had finally captured the final brick of the cosmic architecture, leaving future generations with nothing more than engineering cleanup. Yet, true practitioners of the discipline knew better, recognizing that finishing a puzzle does not mean you understand the forces that manufactured the cardboard box it came in. The Standard Model, for all its undeniable majesty, resembles an exquisitely detailed painting of a house viewed entirely from the front porch, offering zero insight into the plumbing, the electrical wiring, or the deep foundations supporting the structure from underneath. It is a phenomenological triumph rather than a fundamental theory of everything, cobbled together with dozens of arbitrary numerical parameters, masses for quarks and leptons, coupling constants for forces that must be measured by experiment rather than derived from first principles. If you ask the Standard Model why an electron possesses the precise mass it does, the theory shrugs its shoulders and hands you a blank sheet of paper. This glaring deficit has driven generations of theorists to construct grander, more ambitious edifices, stretching the boundaries of human mathematics into realms that border on the esoteric. Among these ambitious frameworks, supersymmetry reigned supreme for decades as the darling of theoretical physics, promising a beautifully symmetrical universe where every known matter particle possessed a heavy, undiscovered bosonic partner, and every force carrier held a fermionic counterpart. Supersymmetry was elegant, mathematically rigid, and possessed an almost hypnotic allure, solving several gnawing quantum puzzles simultaneously, including the notorious hierarchy problem that plagued the mass of the Higgs boson. Theorists spent 30 years calculating the properties of selectors, squarks, winos, and xinos, predicting that the Large Hadron Collider would light up with a breathtaking cascade of exotic new particles the moment it achieved high-energy collisions. Yet, as the collider powered up and pushed toward higher luminosities, the promised supersymmetrical partners failed to materialize, remaining stubbornly absent from every collision debris field. The multi-TeV energy planes, where these particles were expected to dance, turned out to be completely barren, forcing the physics community into a quiet, painful reckoning. The silence of the supersymmetrical desert did not disprove the underlying mathematical beauty of the concept, but it delivered a brutal empirical reminder that nature is under no obligation to conform to human aesthetic preferences. The universe, it turns out, is far more subtle and parsimonious than our most cherished theoretical dreams, preferring bizarre, understated anomalies like the penguin decays of B mesons over the grand cinematic particle explosions envisioned by symmetry enthusiasts. This brings the discussion directly to the broader ecosystem of flavor physics, a specialized subfield that has quietly evolved into the frontline trench of modern scientific inquiry. While high-energy physics focuses on brute force collisions designed to tear the vacuum apart and manufacture heavy particles out of pure kinetic energy, flavor physics operates with the surgical precision of a watchmaker. It investigates the hidden rules governing the generational families of matter, why there are three distinct tiers of quarks and leptons, each identical in charge and spin to its lighter sibling, yet inexplicably bloated with mass. The electron, the muon, and the tau particle share the exact same quantum identity, yet a muon is roughly 200 times heavier than an electron, and a tau is nearly 3,500 times heavier. The Standard Model accepts this bizarre mass hierarchy as an empirical given, but it provides no underlying dynamic to explain why nature decided to repeat its fundamental particle recipe 3 times. This profound ignorance is formally known as the flavor puzzle, and it sits at the absolute center of every modern theoretical crisis. When anomalies arise, they almost invariably appear within flavor-changing processes. Decays, where one quark transforms into another, or where a heavy lepton mutates across generational boundaries. This is not a coincidence. It is because the flavor sector acts as a magnifying glass for physics operating at ultra-high energy scales that are otherwise completely inaccessible to direct human observation. To appreciate how quantum loops can whisper secrets about realms beyond our reach, one must delve into the strange, counterintuitive reality of quantum field theory, where empty space is never truly empty. The vacuum of the universe is a boiling, hyperactive sea of quantum fluctuations, a roiling foam where virtual particles constantly pop into existence and vanish back into nothingness before their presence can be directly registered by any instrument. These fleeting entities are not mathematical fictions. Their cumulative effects dictate the precise properties of stable matter. When a B meson undergoes its rare decay into a kaon, a pion and 2 muons, it momentarily transitions into a virtual state that samples every possible quantum pathway allowed by the laws of nature. If there exists an undiscovered heavy particle, perhaps a leptoquark weighing hundreds of tera-electron volts, or a massive Z-prime gauge boson associated with a hidden force, that particle participates in the quantum foam, altering the transition probability by an infinitesimal fraction. The resulting angular deviation observed by the LHCb detector is the microscopic shadow cast by these unseen giants as they pass momentarily through the quantum loop. This mechanism transforms mundane subatomic debris into an interstellar telescope, allowing researchers on a mud-streaked plain in Switzerland to peer indirectly into energy domains that would otherwise require a particle accelerator the size of the Milky Way galaxy to probe directly. The technological marvel required to capture these microscopic shadows is a triumph of modern engineering that is rarely appreciated outside specialized academic circles. The LHCb detector is a masterclass in asymmetrical design, shaped unlike the giant barrel detectors of Atlas and CMS, which wrap completely around their respective collision points like enormous multi-layered onions. Instead, Because the beam mesons produced at high-energy proton-proton collisions tend to shoot forward along the line of the beam pipe, rather than spraying out spherically in all directions, LHCb is built like a massive forward-facing spectrometer stretching 50 meters down the tunnel. It features sophisticated vertex locators packed with silicon microstrip sensors capable of tracking particle trajectories with a spatial resolution measured in microns, situated mere millimeters away from an intense beam of circulating protons operating in a high radiation environment that would instantly fry conventional electronics. Every single second, millions of collisions are registered, digitized and filtered by a massive real-time farm of graphics processing units that must make split-second decisions about which events to record and which to discard into the digital void. This trigger system operates with ruthless efficiency because out of the staggering deluge of particle wrecks, the specific rare decays of interest are needles buried within hyperdense haystacks of background noise. The sheer volume of data handled by LHCb over its lifetime amounts to petabytes of information, requiring global distributed computing grids linking academic institutions across continents just to process, calibrate, and analyze the raw collision logs. Yet, as the datasets have expanded and the analytical techniques have grown sharper, the psychological toll on the scientific community has become a tangible factor in how these discoveries are handled. Particle physicists are human beings driven by ambition, hope, and the intoxicating desire to leave their mark on history, yet they operate within a professional culture that rigorously penalizes self-deception and premature celebration. This tension gives rise to elaborate institutional safeguards designed to protect researchers from their own enthusiasm, most notably the strict protocols of blind analysis. When a collaboration sets out to measure a delicate angular observable or search for a tiny asymmetry in decay rates, the core analytical code is heavily encrypted or blinded by masking the signal region with randomized offsets, or by injecting artificial data shifts known as SALT. Analysts must refine their software pipelines, simulate detector inefficiencies, model background contaminations, and reach a complete consensus on their methodology while remaining entirely ignorant of what the final answer actually looks like. Only when every single procedure has been locked down, peer-reviewed internally, and formally signed off by the collaboration leadership is the virtual box finally unlocked in a tense conference room session. This deliberate ritual strips away the unconscious bias that naturally leads researchers to tweak cuts and adjust parameters until the data yields the exciting result they secretly hope to see. The heartbreak of discovering that an anomaly has vanished upon unblinding, or conversely, the cautious, heavy realization that a persistent 4 sigma deviation refuses to go away, carries a profound emotional weight that shapes the institutional memory of CERN. The historical shadow of past false alarms hangs heavy over every seminar room and conference presentation where these anomalies are discussed, serving as a sobering reminder of how easily nature can mock human ingenuity. Beyond the famous examples of the faster-than-light neutrino cable blunder or the phantom 700 and giga-electron-volt bump, particle physics is littered with forgotten anomalies that once commanded the covers of scientific magazines before fading into obscurity. In the late 1990s, the LEP accelerator at CERN recorded a baffling excess of events involving pairs of W bosons that briefly hinted at the existence of a heavy, unexpected scalar particle, only for the signal to dilute into statistical noise as more integrated luminosity was gathered. Earlier still, in the 1980s, reports of anomalous peaks in positron spectra from heavy ion collisions at the GSI facility in Germany sparked intense theoretical speculation about extended nuclear states or novel, non-perturbative quantum electrodynamics phenomena, which ultimately traced back to subtle instrumental backgrounds and kinematic effects. These ghost stories teach an unyielding lesson. Statistical fluctuations are remarkably adept at mimicking true physical breakthroughs, and nature possesses an infinite capacity to generate coincidences that look like laws. Consequently, when a modern anomaly like the B meson angular deviation survives 12 years of continuous scrutiny, evading every known instrumental artifact and outliving independent cross-checks by rival detector teams, it forces even the most cynical skeptics to pause and adjust their posture. What makes the current theoretical landscape particularly compelling is that these flavor anomalies do not stand in lonely isolation. They form part of a broader, interconnected tapestry of persistent tensions that have steadily accumulated across various corners of the precision frontier. Consider, for instance, the long-standing saga of the Cabibbo angle anomaly, which involves precise measurements of quark mixing parameters derived from nuclear beta decays. For years, calculations tracking how up quarks transform into down quarks via the weak interaction have hinted at a subtle violation of quark-lepton universality at the very first tier of the generational ladder, hovering persistently around 2 to 3 sigma. While an individual discrepancy of that magnitude can easily be dismissed as an underestimated nuclear correction, its structural alignment with the broader family of flavor puzzles provides a haunting echo. When you pull on a loose thread in the standard model, whether it involves muon magnetic moments, rare B-meson decay angles, or tau-lepton ratios, you frequently find that the thread is attached to a hidden fabric spanning entirely different subfields of physics. This systemic coherence across independent observables is precisely what separates a localized data quirk from a potential systemic failure of the foundational framework. To fully grasp what is theoretically required to resolve these tensions without breaking the entire edifice of established physics, theorists have developed sophisticated frameworks known as effective field theories. When studying phenomena at energy scales far below the mass threshold of undiscovered heavy particles, physicists do not need to know the exact microscopic details of those heavy entities. Instead, they can parameterize their collective effects using higher dimensional operators suppressed by inverse powers of the new physics scale. This mathematical approach allows researchers to remain agnostic about whether the underlying cause is a leptoquark, a Z-prime gauge boson, or some more exotic construct involving extra spatial dimensions or composite Higgs dynamics. By analyzing the global fits of these effective operators across dozens of different decay channels simultaneously, theorists can map out the precise parameter space required to explain the observed anomalies. These global fits reveal a striking convergence. A single new physics scenario involving specific couplings to third-generation quarks and leptons can simultaneously account for the angular deviations in rare B-meson decays, the persistent hints in tau-related processes, and various other subtle asymmetries, binding disparate anomalies into a single, cohesive, explanatory narrative. Yet, even as theorists construct these elegant global fits, the looming specter of theoretical uncertainty reminds everyone involved that human calculation has its limits. The so-called charming penguins, the complex quantum loops involving virtual charm quarks, represent a formidable obstacle that separates an interesting hint from an undeniable revolution. Calculating the strong interaction dynamics of charm quarks inside a looping B-meson decay requires navigating the non-perturbative regime of quantum chromodynamics, where the strong force binds quarks so tightly that standard perturbation theory breaks down completely. Physicists must rely either on heavy quark effective theories, QCD sum rules, or massive lattice simulations running on supercomputers to estimate these contributions. If future algorithmic advancements and computational power breakthroughs reveal that charming penguin contributions are systematically larger than currently estimated, the entire case for new physics could evaporate into a mundane calculation error, proving once again that our map of the wall was simply flawed. Conversely, if lattice QCD calculations continue to confirm that the charm contributions fall well short of the observed angular shifts, the theoretical room for mundane explanations will close entirely, leaving experimental reality standing face to face with an undeniable crack in the foundational laws of nature. This profound methodological struggle highlights a deeper philosophical truth about the scientific enterprise. Progress is rarely a linear accumulation of triumphant certainties. Rather, it is a turbulent dialectic between experimental surprise and theoretical rationalization. Every major paradigm shift in human history, from Newtonian mechanics to general relativity and from classical electrodynamics to quantum mechanics, was born out of an uncomfortable anomaly, a tiny numerical mismatch that polite scientists initially tried to ignore or explain away as experimental sloppiness. The 43 arcsecond perihelion precession of Mercury was dismissed for decades as an unaccounted for dust cloud or a measurement error before Einstein recognized it as the first visible tremor of spacetime curvature. The ultraviolet catastrophe in blackbody radiation was viewed as an awkward mathematical quirk before Max Planck introduced the radical concept of quantization. And in our own era, the stubborn angular lean of dying B mesons and the mysterious flavor puzzles of the three generations may well represent our generation's Mercury anomaly, a microscopic crack in an otherwise flawless intellectual monument, pointing the way toward a vastly richer, deeper understanding of physical reality. As the Large Hadron Collider continues its high luminosity operational phases, pushing accumulated collision data to unprecedented heights, and as next-generation precision facilities like the Bell 2 experiment in Japan gather complementary datasets with alternate systematic uncertainties, the statistical verdict on these flavor anomalies will inevitably sharpen. If the deviation marches steadily past the 5 sigma threshold, crossing the formal boundary of discovery while surviving every theoretical counterattack and computational refinement, the aftermath will trigger a seismic restructuring of theoretical physics. The discovery of a leptoquark, or a fifth fundamental force, would not merely solve a local discrepancy in quark decay rates, it would provide the long-sought empirical anchor for grand unification, offering the first tangible clue as to why the universe possesses 3 generations of matter, how the microscopic laws of the subatomic realm connect to the macroscopic architecture of gravity and cosmology, and why there is something rather than nothing inhabiting our cosmos. Whether this persistent bird-shaped anomaly ultimately proves to be a revolutionary window into uncharted physics or another sophisticated ghost haunting the graveyard of science, the journey itself has already reaffirmed the relentless, beautiful audacity of the human endeavor to decode the universe against all odds.